Hidden Markov models. Hidden Markov models. In a hidden Markov model HMM, the states are not observable, but when we visit a state, an observation is recorded that is a probabilistic function of the state. We assume a discrete observation each state from the set v1, v2, v3 until vm, such that bj of m is approximately equals to the probability of OT, by definition, equals to the probability of OT equals to VM, conditioning on QT equals to SJ, where BJ of M is the observation or emission probability that we observe VM, where M is equals to 1, 2, 3 until capital M in state SJ. We again assume a homogeneous model in which the probabilities do not depend on t. The values thus observed constitute the observation sequence O. The state sequence Q is not observed. That is what makes the model hidden. But it should be inverted from the observation sequence O. Note that there are typically many different state sequences Q that could have generated the same observation sequence O, but with different probabilities. Just as given an IID sample from a normal distribution, there are an infinite number of mu sigma value pairs possible. We are interested in the one having the highest likelihood of generating the sample. Note also that in this case of a hidden Markov model, there are two sources of randomness. In addition to randomly moving from one state to another, the observation in a state is also random. Let us go back to our example. The hidden case corresponds to the arm and ball example where each arm contains balls of different colors. Let Bj of M denote the probability of drawing a ball of color M from arm J. We again observe a sequence of ball colors, but without knowing the sequence of arms from which the balls were drawn. So it is as if now the arms are placed behind a curtain, and somebody picks a ball at random from one of the arms, and show us only the ball without showing us the arm from which it is picked. The ball is returned to the arm to keep the probabilities the same. The number of ball colors may be different from the number of urns. For example, let us say we have 3 urns and the observation sequence is O equals to the set red, red, green, blue, yellow. In the previous case, knowing the observation ball color, we knew the state urn exactly because there were separate urns for separate colors and each urn contained balls of only one color. The observable model is a special case of the hidden Markov model, where m is equals to n, and bj of m is 1 if j is equals to m, and 0 otherwise. But in the case of a hidden model, a ball could have been picked up from any urn. In this case, for the same observation sequence O, there may be many possible state sequences Q that could have generated O. See figure 15.2. To summarize and formalize an HMM has the following elements. 1. N is the number of states in the model. S equals to S1, S2, S3 until Sn. 2 is M. What is M? M is the number of distinct observation symbols in the alphabet. That is V equals to V1, V2, V3 until Vm. And 3. A is the state transition probabilities. A equals to the collections of braces Aij, where entity Aij is defined as the probability of Qt plus 1 equals to Sj, conditioning on Qt equals to Si. And for observation probabilities is equals to B equals to the set Bj of M braces, where Bj of M is defined as the probability of Qt equals to Vm, conditioning on Qt equals to Sj. So the fifth element is the initial state probability. That is pi equals to pi I braces, where pi I is defined as the probability of Q Q1 equals to Si. So it's a collections of probability. And N and M are implicitly defined in the other parameters. So lambda is equals to AB pi is taken as the parameter set of an HMM. Given lambda, the model can be used to generate an arbitrary number of observation sequences of arbitrary length, but as usual, we are interested in the other direction, that of estimating the parameters of the model given a training set of sequences.